Okay, we're going to finish derivatives and calculus with parametric curves or parameterized curves. So the first thing we have to do is we have to look at how to find the second derivative. In the previous video, we ended with finding the first derivative and the formula we used for that. In this section, we're going to work with arc length and a few other things as well. So let's see here. Our formula for the second derivative is d squared y over dx squared. And what this means is you do the derivative of dy dx. So remember, we had to find dy dx by doing dy dt divided by dx dt. Now we're going to have to ddt whatever we got from that, okay? And then we again divide it by dx dt. So this is a formula that you would have to memorize. The derivative of the slope basically is what we're doing for our numerator, and then we're dividing it again by the derivative of the x value. Okay, so make sure you guys memorize this formula. That way, if I gave you an exam question on it, it would be pretty straightforward for you. Okay, so this is the type of question you may be asked. It says, when is x equal cosine squared of t and y equals 1 plus sine of t concave up on the time interval 0 to 2 pi. Remember, that was one of the main focuses of the second derivative for us in Calculus 1, was finding the second derivative so we can work with concavity and points of inflection. So in this particular problem, they just ask us to determine when this will be concave up. So that means I need to find my second derivative. I need to create a sign chart and then determine where the sign chart is positive for the second derivative, and that'll be when I'm concave up. Okay, so the first thing I need to do is I need to find dy dt, and dy dt will be cosine of t. Okay, the next thing I need to do is I need to find dx dt, and dx dt, let me look at this for a second. I gotta move my computer. Dx dt will be worth, let's see here, take the power, put it in front, so that's 2 cosine of t times the derivative of cosine is negative sine t. So we end up getting negative 2 sine t cosine t. Okay, so this is our dy dt divided by dx dt. So that means we now technically know dy dx, which is cosine of t, remember our formula from the previous video, divided by negative 2, which is dx dt, negative 2 sine t cosine t. Okay, so we can clean this up just a little bit, and we have dy dx is worth negative 1/2. I guess we could call this cosecant t if we want it to be as clean as possible. So we're now going to use this to find our second derivative. And remember, the second derivative says d dt divided by dx dt. So we're going to take the derivative of our first derivative, which will be, let's see here, negative 1/2, but the derivative of cosecant is positive, so this is going to turn positive. Cosecant t cotan t divided by, now it says dx dt. Dx dt was negative 2 sine t cosine t. So I'm going to do a little bit of cleanup on this. So this will be, let me see here. It'll be negative 1/4. Now let's see what's left on top. This is a cosecant of t, so that means in the denominator I'm going to put a sine t. So right here I'm working with the cosecant, and I turn that into 1/sine of t. And then the cotan is actually cosine over sine. So this will be cosine of t over sine of t. And then I still have the rest of this. I already used the 2 up, but I have to deal with the sine and cosine. So sine t cosine t. So that is actually, let's see here, the cosine cancels, left with 1. So we end up with 1/4, negative 1 over 4, sine cubed t. I could write this a little better. Negative 1 over 4 sine cubed t. Okay, so we have that. Now remember, our job, this is now our second derivative. Our job is to find when the second derivative is d and e, or where it's 0. So we're going to find out when is sine of t equal to 0. So basically all I'm doing is I'm looking at this, and I don't need the cubed. The cubed is not going to affect whether it's 0 or not. It's all about the sine of t. So we know that sine of t equals 0 when t equals what? Well, t could be 0, or t could be pi, or t could be 2 pi. Okay, those are all instances where sine would equal 0. However, I'm really only going to focus on the pi because remember, 0 and 2 pi is the end of our interval, and those really can't be changes in concavity, right? Because we'd need something to the left or right of them to say. So I'm really going to focus on, and also on top of that, we're only talking between 0 and 2 pi, so we don't even know what's going to happen on the other side. So what I'm going to do is I'm going to just put pi here in the middle, and I'm just going to do a second derivative test on my, I guess you would call this d squared y over dx squared. Okay, so I'm going to plug something to the left of pi in. When I plug something to the left of pi in, I will get a negative. When I plug something into the right of pi, like say 3 pi halves, 3 pi halves, take the sine of 3 pi halves, and that'll be negative 1. Negative 1 cubed is still negative 1. And then we have negative 1 over negative 4, which will become positive. Okay, so that means that we have concave down right here, and we have concave up here. So the problem wants to know when are we concave up. So we're going to say concave up on the interval from pi to 2 pi. Okay, and that is when we are concave up. So we answered their question. Okay, let's see here. Do we want to try this other one? Let's take a look at this one. I think I have another good one for you guys. So let's look at example 2. Okay, so it says find d squared y over dx squared. Okay, of, and then I'm going to tell you what x is worth. X is worth 1 minus t squared, and y is worth t to the 7th plus t to the 5th. So I'm not asking for concavity this time. I'm just asking you to find me the second derivative. Okay, so we know that dy dt is something we'll need, and we know we will also need dx dt. So pause the video and see if you guys can find the second derivative of this without my help. And then when you're done, unpause it, and let's kind of go through it together and see if we end up in the same spot. Okay, so hopefully you guys are back from the video now, from the pause, I should say, and are coming back to the video. So dy dt is worth 7t to the 6th plus 5t to the 4th. dx dt is worth negative 2. Okay, so then I'm going to find dy dx is equal to 7t to the 6th plus 5t to the 4th divided by negative 2t. Okay, let's clean this up just a little. I can take a t from this and become a 3. I can take a t from that and become a 4. And then I can throw the negative on top. So this will be a negative 7t to the 5th. You know what I can do? We can do negative 7 over 2 t to the 5th minus 5 over 2 I think that'll be an easier way to write it. Maybe I should put this one. Both of these in the middle since I did it for one of them. Okay, so negative 7/2 t to the 5th minus 5/2 t cubed. Okay, so this is my dy dx. And remember, d squared y over dx squared, the second derivative, is the derivative of that. So I'm going to ddt negative 7 over 2 t to the 5th minus 5 over 2 t cubed. And I'm going to divide that by dx dt, which is negative 2t. Okay, so let's get some cleanup here. The first derivative, or the derivative of that would be what, negative 35 over 2 t to the 4th minus 15 over 2 t squared, all divided by negative 2t. So let's see what we have now. When we clean this thing by, okay, so we're going to have negative 35 t to the 4th minus 15. I guess we could do this, 15t, t squared all over 2 divided by negative 2t is the same as multiplying by 1 over 2t negative. And that will become 35 t cubed plus 15t all over 4. Because this t is going to cancel with each one of those. So we end up with 35t to the 3rd plus 15t all divided by 4. So this would be my second derivative. Okay. So take a minute, make sure you're caught up. Okay. So now let's look at a second style of problem. We're now going to look at arc length. So if you remember from chapter 8, in Calculus 1, you guys probably talked about arc length with your teacher. If your teacher ran out of time, sometimes that's a topic that sometimes are covered. But we're going to basically do the same thing that you learned with arc length in chapter 8, just finding the length of an arc. We're going to use that same concept of doing an infinite number of little triangles and their little arc, or the little lengths of those. We're going to use that same concept to help us deal with parametric curves, okay? So this is going to be our arc length formula that you also need to memorize. L equals the integral from a to b of the square root of dx dt squared plus dy dt squared dt. And this is basically almost identical to the arc length formula from chapter 8, okay? The upper and lower limits in these problems, A and B, are time values. So our upper, our integration, time values, because we're dealing with t. This is more of a formula problem where we can kind of plug and chug. So it says, example 3. Let's find, now some of these are pretty long-winded, so I hope you leave yourself a little bit of space. So find the length of x equals cosine cubed t, y equals sine cubed t, or 0 less than or equal to, let's see here, t less than or equal to pi halves. Okay, so I'm asking you to find the length of the curve x equals cosine cubed t and y equals sine cubed t on the time interval from 0 to pi halves. So let's see. The formula says that we're going to need dx dt and dy dt. So I'm going to find dx dt first. And that will be 3 cosine squared t times the derivative of cosine of t, which is negative sine t. Okay. And then dy dt is equal to 3 sine squared t times the derivative of sine, which is cosine t. So we have sine squared t cosine t. And I can just clean this up a little. This will be negative 3. I guess I could write the sine first. Sine t cosine squared t. And this one, I'll just write the cosine first. 3 cosine t sine squared t. It's just a preference, but we now have the derivative of each, right? So now we can come back, and it says that we plug these into the square root formula. So let's integrate these. It says L equals the integral from 0, the time interval given, okay? And then I am going to take the square root of dx dt squared. So dx dt, so that would be 9 sine squared t cosine to the 4th t. And then it says we add plus 9 cosine squared t sine to the 4th t dt. Okay. Now let's see if there's anything we can factor out. In general, if you remember from back in your Calc 1 class with these type of problems, a lot of times the square root causes the issue. So you're trying to find a way to create some kind of perfect square under there or something with factoring so you can get rid of the square root, because otherwise the integration is nearly impossible. Okay, so I'm going to factor out a 9. They both for sure have a 9 in common. They both also have a sine squared and a cosine squared in common. So sine squared t cosine squared t. And let's write the leftovers. So when I take a 9 sine squared t cosine squared t from that, that's going to leave me with a cosine squared t, right? And then when I take a 9 sine squared cosine squared from this, that's going to leave me a sine squared t. Now that actually looks really good, because you guys should be thinking right now, what is cosine squared t plus sine squared t? Well, that's just 1. So we now have L equals 0 pi over 2, the integral, of 9 sine squared t cosine squared t times 1, which is great. And then we can rewrite this as the square root, the integral from 0 to pi halves. Now notice these are all perfect squares and they're being multiplied, so I can actually square root this. And it'll be 3 sine t cosine t, okay? And we're going to do a little basic u sub for this. We're going to say u equals, I don't know, I think you could do it either way, but I'm going to say sine of t, and then du is equal to cosine of t dt. So now we're going to say L is worth, I guess we could change the limits of integration as well. So if we come over here, if we say u is equal to sine of t, that means we say u equals the sine of 0 and u equals the sine of pi over 2. So in this case, u would be 0, and in this case, u would be 1. So I could use from 0 to 1. That would make my life a little bit easier. And I'm going to take, and I'm going to pull the 3 out, and this becomes the integral of u du. Now that is going to be 3 times u squared over 2, 0 to 1. You know what? I can even clean this up better. Let's just do 3 halves u squared from 0 to 1. So this will be 3 halves times 1 minus 0, which is 3 halves. Okay, so we get 3 halves as our arc length. So this is a pretty straightforward problem. It's just a little bit long-winded. In general, this kind of process is going to happen, you're going to always be looking for some kind of combination of sine squareds and cosine squareds, or some identity in general when you're working with your homework or on the exam. There's always something little that you can do to clean these up. And then you're hoping at the end that you get a nice, easy integral like that, okay? That's kind of the goal. If you don't get a nice, easy integral, you're in a little bit of trouble, okay? So that's an arc length problem. Now let's look at a surface area problem. And again, this will feel very similar to those of you that had this in Calc 1. Example 4. You know, we need surface area. This will feel very similar to the problems you did in that class. So we have surface area. So we have rotation about x-axis, and that will be 2 pi times the integral from a to b of y times the square root of dx over dt squared, okay, plus, you guessed it, dy dt squared dt, okay? And very similarly to Calc 1, you're thinking of this idea. It's almost like, I guess you're putting you have this little tiny arc length, and then you're basically going to say that you're going to wrap this little tiny arc length, you're going to stretch it all the way around something, you're going to rotate it, okay, around something, and that'll cover the surface of it. Now, how many of these arc lengths do you have? You approach an infinite amount of them. So you're going to be wrapping every single one of these. You know, this is all mental. You can't actually do this. But you're taking these little strips, and it's almost like it's a piece of tape, and you're wrapping it around the object. And if you're wrapping it around in rotation with respect to the x-axis, then you use y. So this is basically 2 pi times r times the arc length, okay? So we're going to go ahead and have this one, and then we'll also have rotation about the y-axis. So we have a formula for this as well. Okay, so this will be 2 pi integral from a to b of x times the square root of dx squared plus dy dt squared dt. Okay, and it just depends on what you're working with. All right, so let's look at this problem. And again, these problems are in terms of t, so you will be substituting in t values. I think we need to do one so you guys can kind of see what I'm talking about. So find example 4, I believe. Let's see. Yep, example 4. So it says find the surface area x equals a cosine of t, y equals a sine of t, 0 to t equal to pi. So in this problem, they want you to kind of see there's almost like a little formula that results from this idea. Okay, so it says find the surface area when x equals a cosine of t and a sine of t. So we're going to come over here and we're going to find dx dt, and we're going to find dy dt, because we know for our, whether we're doing arc length or whether we're doing surface area, we need the dx dt and the dy dt. Basically, again, you're using the arc length formula, and then you're wrapping it around the object, depending on which way you're rotating. And that's how we're doing this 2 pi. We're making one full revolution. Okay, how much would it take to rotate all the way around? Okay, so we have dx dt is equal, now you're considering these a's, we're going to consider these constants. Okay, so we're going to use the constant multiple rule on these, not the product rule. And so this will be negative A sine t, and this will be A cosine t. Okay. And then we're going to plug this in to our integral formula. So surface area equals 2 pi times the integral from 0 to pi, right, of, now we have to square root, and then we're going to take dx dt squared. So this will be a squared sine squared t plus a squared cosine squared t dt. So we have our surface area equals 2 pi times the integral from 0 to pi. Now we can definitely factor out an a squared, and this will leave me with sine squared t plus cosine squared t dt. Now, once again, hopefully you guys are starting to see this pattern that happens quite often, not every time, but it happens a lot. Sine squared plus cosine squared is sine squared t plus cosine squared t is equal to 1. So we now have 2 pi times the integral from 0 to pi of a, and that's it, right, of a dt, right? Because you're just basically left with, well, I guess I should write out another step so I don't lose you guys. I don't want to upset you and say, Professor, why didn't you show that last step? But that's, the square root of a squared. So then this will be, 2 pi integral 0 to pi of a dt. Now you guys got it from here, right? So this will be 2 pi a squared over 2 from 0. No. I was treating a as a variable. It is not. It is a constant. So this is 2 pi a t from 0 to pi. I feel like I lost something. Let me just hold on here. Oh, you guys, do you notice my mistake? I made a little silly mistake. I didn't write the formula correctly. Let's look way up here into my formula. We are rotating. I did not tell you sine t from 0 to t is less than or equal to pi. Rotated. See, this is why I didn't finish the question. Is rotated around. That's a mistake on my part, so please let's go back and fix that. If it's rotated around the x-axis, we use y. So we know in this particular problem, y is worth a sine t. So let me go back to here. So there's actually supposed to be a sine t here, and a, I'm just going to erase it all. I messed it up, so I might as well pay the price. So let me write this again. A sine t times the square root of a squared sine squared t plus a squared cosine squared t. So that's what happens. That's the price I pay for not writing the formula out correctly. So I think we're good now. So I should have an a sine of t right there. Now the thing is that technically that a is a constant. So realistically, I could pull that out at any time, but I'm just going to see what we have here, a sine of t. Now we know that we can factor this like we did last time. Okay, so it would be a sine t times the square root of a squared, right? Because this is just going to be 1. But that's really 2 pi times the integral from 0 to pi of, what is that, a squared sine t. Okay, so now surface area equals, now let's scroll up a little bit, 2 pi. Now here's the thing, I can now take this a squared out, and I'm left with the integral of 0 to pi of sine t. But once again, this is a very doable integral, but you guys see what I mean by these problems are long-winded. We're just doing a lot here, little steps. There's obviously a few steps you guys could have skipped. I probably would have skipped 2 steps in here, but I'm trying to show you guys, especially after I already messed up, I'm trying to show you guys the right way to do it. Okay, so we are now left with 2 pi a squared, the integral, times the integral from 0 to pi of sine of t, which we know is 2 pi a squared times the integral of sine of t, which we can integrate now and become negative cosine of t from 0. Now, if I wanted, I could take that negative out, so it would be negative 2 pi a. You know what? I don't even care. I'm not going to take that. I'll just leave it 2 pi a squared. And let's see, the cosine of pi is -1, but it's a negative cosine, so that becomes 1. Okay, and then the cosine of 0 is 1, so minus 1. This becomes what, 2, so this will actually become 4 pi a squared. Okay, so this is how we can find the surface area. So this is our surface area. This is 2. I think we can do one more of these. I think this one's a little bit worse. Let's see. Let's take a look at another one. So it says find surface area when x equals 2/3 t to the 3/2, comma, y equals 2t square roots of t. 2 squared to t from 0 less than or equal to t less than or equal to square root of 3 is rotated around the y-axis. So we'll go this way. Let's look at this. This is example 5. Oops. Got example 5. Okay, so we, just like before, we know we're going to need our arc length formula, so we know we're going to need dx dt equals, so this will be 2/3 times 3/2 t to the 1/2, I believe. Let's see here. And then dy dt is going to equal 2 times 1/2 t to the -1. So this will become t to the 1/2. This will become 1 over t to the 1/2. Or we could leave it as t to the -1. We'll leave it as t to the -1. Okay. So now we're going to use our surface area formula, and we know that's going to be 2 pi times the integral from 0 to square root of 3. So take a minute, you guys, pause the video, and see if you can go from here. And don't forget what I did in the last step. Don't forget to use your x. Okay? You have to, in this case, because you're rotating around the y-axis, we go to our formula. If we're rotating around the y-axis, we use x. Okay, so oops. So go ahead and pause the video and see how much you can get done. Okay, hopefully you guys are back. And now we have to plug in. So we know we're going to use x this time. I'm not going to mess that up. So this is 2/3 t to the 3/2 times the square root of something dt. So we're going to plug in 2/3. Oh no, it's just t to the 1/2. So I'll just plug in t to the 1/2 squared plus t to the -1/2 squared. So surface area equals 2 pi 0 to the square root of 3. You know, I'm going to take that 2/3 out right now too. This will be 4/3 3/2 the square root of t plus 1 over t dt. Well, so this one is harder, not because the beginning was harder, but because this integration step is a little harder. Now, there's quite a few ways you could look at this. In general, a technique that I've kind of found that works would be in general to I guess we could turn this t to the 3/2 into a actual radical. And let's see how that would work. I don't know if that's the best choice. Let's try this. 4/3 pi from 0 to the square root of 3. And I'm going to call this t cubed square rooted times the square root of, I'm going to make common denominators in here. Sometimes this is a good go-to move inside your radical. Sometimes it works, sometimes it doesn't. So this will become t squared plus 1 over t. And this is still the same thing as before. I just rewrote it with common denominators. As it turns out, now I can rewrite this as surface area equals 4/3 pi from 0 to the square root of 3. They both are square roots, so I can combine them. So this will be one big square root, and this will be t to the 5th. You know what I could do? I could cancel. You know what? I'm going to save it. This will be t to the 5th plus t cubed all over t dt. Let me hold on one second. Let me close the Okay. So, let's see here. I can clean that up some more even. And again, sometimes you end up dancing in a circle and it doesn't get you anywhere, but I think this will get us where we want to go. Oh yeah, this is going to do it. Okay, so all I did here, for those of you that are watching this, is I divided both by t. There's, like I said, there's multiple ways. I could have done it also here. I could have canceled this and this if I wanted, but I just chose to do it this other way. 4/3 pi, 0 to the square root of 3. This is going to become t squared times t squared plus 1 dt. Now, I hope you guys are, once again, what I was talking about, long-winded. Here we keep going. You know, how many steps is this? As a teacher, I'm probably writing out more steps than you will, student. You'd probably be skipping around a little. So this will become t square root t squared plus 1. And you might say, well, man, are we doing like arcsine or arctan or something? No, because we can just do a nice u sub now. We say u equals t squared plus 1. So then du is equal to 2t dt. Divide both sides by 2. And we have our t dt, which is our t dt right there. Okay, so we have a perfect match. So let's keep going. So this becomes d over 2. I'm going to bring the 1/2 out. So this will become 2/3 pi because they cancel. 0 to square root of 3. And here I'm with u to the 1/2 du. Okay, and I technically should change my numeration. Okay, so let me change these. If u is equal to t squared plus 1, when t equals 0, then u equals 1, so this will be 1. And when t equals square root of 3, then u equals, what, 4? We're going to go to 4. Okay, which is actually good because there's going to be some kind of a square root situation going on here. So we have surface area equals 2/3 pi times u to the 3/2 over 3/2 from 1 to 4. So that 3/2 is the same as multiplying by 2. So this is going to become 4/9 times, what is this, u to the 3/2. I'm sorry. 4 to the 3/2 minus 1 to the 3/2. Okay, so surface area equals, oops, and I forgot the pi. Sorry about that. So this is 4/9 pi times, this would be what? 4 squared is 2, 2 cubed is 8, minus 1, which is 7. So this is going to become 28 pi over 9. hopefully I didn't make any mistakes in it, but that should be our arc length. So it's 28 pi over 9, and so that is the correct answer. So once again, you guys look at what we had to do. These are definitely not easy problems. These require lots and lots of steps, lots of cleanup, okay? But this should get you through chapter 10.2. 10.1 and 10.2 should now be done, and you can deal with parametric equations by graphing them. You can eliminate parameters. You can find the tangent lines to them at given points. You can find their slope, and now you can find concavity, and now you can find their arc length, and you can also find their surface area. And remember, the thing about this is the parameter is t in most of these problems. Every once in a while, it's also theta. But what they're saying is that, yes, we know that it might generate an entire circle or it might generate a parabola, but we only want to know on the certain interval how much of the parabola would be created, you know, from 0 to 2 pi, or from, you know, if you're doing this, some other shape from 1 to 5. T is in between 1 and 5. So the parameter is dictating how much of the graph is showing itself, how much of it is presenting itself to us. And it also is telling us what direction it's being built in. Where did it start versus where is it going? Okay, so that's parametric equations. We'll start the next video with polar coordinates and polar equations, okay? And polar graphs. And that'll do it for this video.